The last 5 electron pair case is a case where 2 of the 5 electron pairs are bonding and 3 are non-bonding. So 2 bonding, 3 non-bonding, and in this regard we take the triiodide ion I3 minus as an example. So I3 minus as an example of this category, and for that obviously we need to draw a possible Lewis structure for which we need to calculate the valence electrons. So 3 times 7, each iodine contributes 7 valence electrons because iodine is a halogen. It's located in group 7A. So the number of valence electrons is 7. We multiply that by 3. If you look at the triiodide ion, it is charged. It's an ion actually. So what we need to do, since the charge is negative, is to add, and we add the same magnitude. So plus 1. So 3 times 7 plus 1, that is 22 electrons, valence electrons total in this triiodide ion. If you divide 22 by 2, we get 11 electron pairs. So there are 11 electron pairs in this triiodide ion. We need this information again to serve us as guides or guidelines in order to be able to predict a possible Lewis structure, for which we begin with the central atom, which is iodine. So this is iodine, and iodine should be bonded to 2 additional iodine atoms. So that's one of them, and that's another. Next step would be, as you might expect, is to draw a bond between the central iodine atom and each of these surrounding iodine atoms. The following step would be to satisfy the octet for each of these 2 iodine or 2 surrounding iodine atoms. So we need to draw therefore 6 electrons on each of them. So that's 8 for that iodine, 8 for this iodine. Each of these iodine atoms is now surrounded by 8 electrons, and that's again in accordance with valency rules, specifically the octet rule. But if you calculate the number of valence electrons used up so far in this Lewis structure, you would find it's actually 16. So 16 valence electrons of the 22 have been used. So we have 6 to go, 6 electrons to go, and these should be represented in the form of lone pairs, so or non-bonding pairs, if you like. So these are the 6 remaining electrons on the central iodine atoms. If you double check, 8 electrons on each of these iodine atoms, each of these surrounding iodine atoms. So 8 plus 8, that's 6, and there are additional 6 non-bonding electrons, so that is 22. So that's reasonable. If you double check the electron pairs, you would find there are 4 here, 4 here, that's 8, plus 3, that's 11, and that's in accordance with the number that we have found before. The last bit left is to draw the whole structure, the whole Lewis structure within square brackets, and then to indicate the charge outside the square brackets on the top right corner. So this is a possible Lewis structure for the triiodide ion. Now the arrangement of electron pairs is still trigonal bipyramidal, because there are 5 electron pairs around the central iodine atom, 1, 2, and 3 lone pairs. So that's 5, but the molecular shape may not be trigonal bipyramidal, but that's because there are 3 lone pairs. So what we need to do is we need to take 3 of these off, and if we do, it's clearly a linear shape. So that's the iodine central atom, that's 1 lone pair, that's another, and that's a third one. These are the surrounding iodine atoms, and if you look at this shape, it's clearly linear, and also the bond angle is obviously 180 degrees. So therefore, the molecular shape in this case, in the triiodide ion case, is actually linear. In conclusion, in this 5 electron pair case, where 2 of the electron pairs are bonding and 3 of them where non-bonding, as exemplified by the triiodide ion, the orbital shape is still trigonal bipyramidal, whereas the molecular shape is linear to take into account the presence of 3 lone pairs around the central iodine atom.